Hello, everyone. Good afternoon. My name is Marcello, as you comment. And today I'm going to speaking about parametric amplification for witness non-Gaussianity, one work which has been done in collaboration with Palak University in Olomouc. And let me start first introducing very quickly what is non-Gaussian states. So non-Gaussian states are states which cannot be written as a convex combination of Gaussian states. In other words, you cannot generate non-Gaussian just by the operation as displacement and squeezing. So example of non-Gaussian state are Fock states or catch states or GKP states. As you can see here on top right, we have a Wigner function of a catch state. And you can see, for instance, one characteristic to the negativity of the Wigner function. Why non-Gaussian? Non-Gaussian research, important research in quantum information processing, as for instance, quantum error correction, entanglement distillation, and universal quantum computation. So it's well known how to generate optical non-Gaussian states. Here, for instance, we have one example where you have a low gain OPA and you generate spontaneous parametric down conversion, and you herald in one of your photon pairs, and then you generate a single photon here, which is a non-Gaussian state. Otherwise, you can also generate by photon subtraction from a squeeze vacuum state. So you can do this photon subtraction in two different ways. You can have a low reflective beam splitter following by the photon detectors, or you can go for a more accuracy way, which is based on nonlinear process, for instance, a up-converted. The last way to generate non-Gaussianity, you can also do photon addition. But besides to generate it, we should be able to certify that we indeed generate a non-Gaussian state. So the first way to thinking about was the Hudson theorem, what we related the negativity of the Wigner function with the non-Gaussianity, which means that if you see the negativity, you can directly say that your state is non-Gaussian. However, this is really good for pure state, but if you go for mixer states, where you have, for instance, vacuum contribution or single photon, or you have a multi-photon contribution generated by your source, this cannot be a very well done certification, because even though your state is non-Gaussian, they can have like Wigner function positivity doing the losses. So in 2011, Radin came with a certification which is based on HBT scheme, which basically measure the probability to have a vacuum, single photon, and multi-photon contribution. So this is showing in this plot the certification protocol to have P0 and P1. The green area are non-Gaussian, the blue area are non-classically. The shadow here, which call non-physical region, where the sum of P0 and P1 is bigger than 1. And in the inset, you can see the probability to single photon as a function of the multi-photon contribution. So basically, if you respect this inequality, you can say about non-classicality and non-Gaussianity, which means that for non-Gaussian state, if your right side is bigger than your multi-photon contribution, your state should be in the non-Gaussian region. However, for this experimental scheme, it's limited for FOC3. So then came up the idea of how the parametric amplification could be used to witness non-Gaussianity. And then, before answer, let me briefly introduce an optical parametric amplification that was before discussed. But here, I just want to stress that, for instance, a parametric down conversion is one example of parametric amplifier. And what a parametric amplifier does, amplifies. That's the main idea. So we amplify and we measure by direct detection the mean number of photons. It can be seen in this image, one example on how we check this amplification. So here what we have the mean number of photons as a function of the Fock state. For a given gain, if you, before you amplify, you have a vacuum and you amplify the vacuum, you should have a mean number of photon proportional to SIMT square of your gain. However, if you see this amplifier with a single photon, you should expect that the mean number of photons increases 3 times, and with 2 photons, 5 times, and so and so. So basically, the mean number of photons can tell you the information of the state before amplification. But a more stronger tool to check is the G2, or the second order correlation function. So if we have a single mode amplified vacuum, we should have a G2 equal to 3 after amplification. However, if you seed with a single photon, the G2 will drop up to 1.6, seeing that your amplifier before had a single photon in the input. So those are the figure of merit to witness non-Gaussianity. And what is our proposal then? We propose to change those two detectors by amplification, following by directly detection. So before showing the amplification, let me first show how do we characterize the multi-photon contribution of our source. So we have a type 2 parametric down conversion generated in photon pairs, degenerated in wavelength, but with polarization and cross-polarization in Ziegler and Idler. One of them are heralding here in this arm, and the other one is sent to the HBT measure, like two-fold coincidences. So what we do, we change the brightness of our source, change how we pump the parametric down conversion. So this increases the multi-photon contribution. So we scan this, as here you can see an example of a coincidence measure when you deal with pulsed lasers. So here you have on the peak the true coincidences, and the sidebands are the accidental coincidence, which appears exactly on the repetition rate of our laser. In our case, is 5 kilohertz. And bottom here is the protocol, the certification, right, for 39% Herald efficiency. So you can see that increase the brightness, the states become to more closer to the boundary region of non-Gaussianity, right? So as we know our source, we can now come to the actually the experimental scheme based on parametric amplification, phase-sensitive parametric amplification. So we generate in the photon pairs, as I comment, one of them heralded, the other photon descends to the amplifier. But first thing that we do, we measure in the vacuum, amplifier vacuum. Because why? Because we want to check the G2 of the amplifier vacuum. So we block and generate the amplifier in the vacuum and strongly filter to generate a single mode. Afterwards, we up the type 2, the parametric down conversion, and then we seed with the single photon. You can observe here the effect of the seeding in the 35,000 pulse measurement and the mean number of photons per pulse. Further, we measure thermal light. For thermal light, now our single photon detector does not trigger the camera to open the exposure time and get the radiation come from amplification. So it's free running. With this enhanced, we can see the very nice effect of amplification, where you can see here the photon number distribution, the probability, in terms of the number of photons. So on the dashed black line, what do we have? Pure single photon. That is the probability distribution for a pure single photon. Button on dot, you have the amplified vacuum probability distribution. Solid line are the experimental results for amplified single mode vacuum. And the magna line here is actually our experiment. So what it shows us, it shows us that our amplification is being sensitive to what we are seeding to the amplifier by the displacement of this photon number distribution. However, the main figure of merit of the witness non-Gaussianity is the second order correlation function. So here you have the second order correlation function in terms of the amplified mean number of photons. What do we have? Horizontal lines, as you can see here, 40, 30, 20, 10, they are the efficiency of our amplification, right? And we are laid down on the 26% efficiency. What we do next, we change the brightness of the source to increase the multi-photon contribution. Up, you see thermal light, and bottom, you see single photon. So we start to increase the brightness of our source, and you see that up to 100 hertz, or the probability of photon number per pulse, it's 0.02, we still lay on the non-Gaussian region. But increasing even further, we go for non-classical region. And if you increase even more, we go to classical region. So that's the figure of merit to witness the non-Gaussianity, in this case for a quasi-single photon, using phase sensitive amplification. So that's the take-home message that I would like to leave in this talk, which means that an optical parametric amplification can be a device to witness non-Gaussianity. Thanks for your attention.
And we are open for questions.
Sorry.
There's a question.
So what specific feature in the statistics witnesses Gaussianity and non-Gaussianity, and can it be replicated somehow with a Gaussian state?
Yeah, that's a good question, and thanks to ask about that. So that actually works pretty well for phase invariant non-Gaussian states, which means that the Wigner function are symmetric. So if you go for phase sensitive, phase variant non-Gaussian states, this G2 will change. So you cannot see, because here we just measure one quadrature. So if you change it, the statistic would be different. But we are looking for the feature to be inside of this non-Gaussian region. That's the point. For instance, thermal light, there are Gaussian states in the outside of this region. But for these phase insensitive invariant non-Gaussian states, you can easily distinguish them. But of course, if you can generalize, but it will not be just one OPA, because you need to measure P and X quadrature if you want to see G2 for a phase invariant state, non-Gaussian.
For drawing these bounds, do you need to make an assumption about the G value, like yourself? I imagine like this green area and blue area are drawn based on what is the G value in the amplification, right?
Before the amplifier, I mean the state?
No, after the amplification, right?
I didn't get. Can you repeat, please?
So you said like the green area is like non-Gaussian and the blue is like non-classical, and obviously the white is classical, right? So are these theoretical like bounds that you drawn based on assuming that this is the G of my amplifier, or you have measured the G of the amplifier?
The amplifier. Yeah, the only assumption that we consider is that the state is phase invariant. There is no assumption of more than it.
And it's time to move. So thank you for your talk.
Thanks.